Go. Hello and welcome to line integrals. Finally, everything converges right here. Previously, the volume and everything else, you can approximate, you can measure. There are ways in which you can figure out things rather than doing integration, but these integrals are going to do something really cool. They're going to calculate the area of a curtain. Now, why would we care about that? Well, see, the trick is that curtain is not a flat object. If I want to find the area of the tabletop, I can just measure the length and the width, and it's a rectangle, and multiply, and I'm done. No need for integration. Triangles can be also completed into rectangle, measure, calculate, done. A lot of stuff you can do and avoid integration completely, and you can approximate. But let's say you have a steel or a curtain made out of glass or some kind of surface like that. It doesn't have to be a curtain. Curtain is the easiest to understand. What is the area of that curtain? Because it's not a flat object that you can actually, it's not a flat object that you can measure with a tape measure and just deal with it as a rectangle. See, when you are sitting in a 3D space like this, X, Y, Z, we are using our right-hand coordinate system as always. The curtain is going to have some kind of irregular shape, and we'll call that the curve C. That curve C lives in the XY plane. On top of that curve C, there is going to be some kind of a curtain, and then the top is going to be given that this line is going to live on some kind of a surface, and that surface is given by Z equals f of xy. So we want to calculate the area of the curtain. And that is going to be calculated using the integral, and we put this C, right, of f, and we are going to denote this as f of xy ds, and I just need to show all of these little pieces. So if you take one of these right here, and you have the height given by f of xk, yk, whatever those values are. So it's the standard. So the whole thing is out. Okay, it's back. Good. So we don't calculate things in terms of the parameter. We calculate, and this is the theorem where you are, which is why we need to know parameterization. Well, let's do the 2D case first. times the magnitude of r prime, and then dt. So this is the line integral formula. Use this to compute line integrals. Now, few things that we need. 12, section 1, and we need to remember 12. That was our first day, guys, first day. And then the next three are all spelled out. Vector r, vector valued function, which is the collection of your parametric equations. And then you go and find r prime, simply derivative of components, and then the magnitude of r prime. Now, some of you will remember that this is speed if you write the speed v. It's not a vector, right? It's a scalar. Vector v with the arrow would be the vector, and that's velocity, and that's r prime. The magnitude of r prime is the velocity. All right, so we can calculate a lot of good stuff with this. I'm just going to say, note in red, C is the curve we parametricize. All right, so that's a note there, so you know exactly where we're going with this. So here it is, the average temp. I like this. So average temp on a circle. So temperature of the circular plate R. So we have the unit circle. You know what? I'm going to do it this way. C equals unit circle. You know that that's x squared plus y squared equal 1. I don't have to tell you that at this point in life. And the temperature distribution function is given as 100 x squared plus 2y squared. This plays the role of f of xy in this particular problem, and this is where your C is. So that's all you need. Step number 1. First, get R of t. Parametrization is extremely important. You can't do anything without it. So, unit circle, the word circle triggers x equals r cosine t, y equal r sine t, equals 1 because it's unit circle. So we get our parametrization as x equals 1 cosine t, so just cosine t, and y equals 1 sine t because it's a unit circle. If the radius was 3, then it will be 3 cosine t, 3 sine t. So you have to be careful about that. So we have the parametrization, and now that one gives rise to our r of t because we take these parametric equations and we stuff them in the vector. So whatever your curve C is, You will make parametric equations for it, and then you stuff those into R. Once you have R, we are switching now to a different color. I get R prime of t, which will be negative sine t cosine t, and then I get the R prime magnitude, which is negative sine t squared plus cosine squared t, which is 1. Now, parametrization has another component which I neglected, 0 and 2 pi. This is important because the blah blah blah. Your parametrization has to have these. You don't want them infinite, because you will be calculating a curtain that's infinite in length. Well, yeah, in that case, it's infinite, right? So your parametrization is going to be over a line segment which has the beginning and the end, circle, 0 to 2 pi to go once around, right? So your parametrization will have to include this component where you are going to have a and b values, and those a and b are used in the integral. So now finally, the step number 3 is to compute the line integral, which is the line integral over the curve C of function f, which is our big T, temperature. So technically, if you want to write this for our problem, it would look like this, because f is t. What I have is the line integral from a to b, that's 0 to 2 pi. Those are my a and b. And now I need my function here, which was x squared plus 2y squared or 3y squared? Oh, and there was 100 in front. Oops. 100 in front. There we go. 100x squared plus 2y squared times 1 dt. So here's your function t of xy. Here's your magnitude r prime, and then dt. So all I need to do is to solve this integral, and you can see this is a basic integral. Now, this integral has to be done in respect to t, so I have to replace x squared with x is cosine in our parametrization, so cosine squared x plus 2 sine squared x. And, oh, sorry, these are not x's, these are t's. T, d, t. It's times 1. That's all gone. So, yeah, you can go ahead and use the power reducing formula, but then you can also do something a little bit more clever, at least to reduce the amount of the formula you have to use. You see, you can write sine over here as sine squared plus sine squared, right? Sine squared t plus sine squared t. So, and then you combine one cosine with one sine, so that will give you 1 plus sine squared t dt. So that reduces calculations a little bit. You don't have to convert cosine and sine and all that stuff. You just convert one of these. Using the power reducing formula from all the way from pre-calculus, from trig course, which is 1 plus 1/2 1 minus cosine 2t, and now everything dt. 100, 0 to 2 pi, open parenthesis, and now I have 1 plus 1/2 is 3/2 minus 1/2 cosine 2t dt. This is when you simplify everything, and now we have just to integrate. So 100 3/2 t minus 1/4 sine 2t from 0 to 2 pi, And when you plug in 0 or 2 pi into a t over here, that's just going to go to 0. So any multiple of pi and obviously 0, sine of those is always 0. So all I need to do is to calculate 100 and then 3/2 times 2 pi, because the 0 is going to get us there. So we have 300 pi. And that would be the average temperature on a circle. Hello, mechanical engineers. These problems tend to be long, and you have to be very careful where you plug and what you plug in. This is where we begin. You have a function, and you have the line over which you are computing. You first parametricize C, which gives you R. So that was the first step, to obtain the R. The second step, don't forget the limits, which will be A and B. The second step of the problem is to obtain R prime magnitude, which we need for the integral. And then the third part is to plug everything in and work out the integral. So all of these components worked out together to get us into the position to calculate this line integral. Let's take a look at another example. Now, before we do that, I'm just going to write the theorem. So this is R3 line integral. And we have, again, the integral C f ds is going to be the integral a to b. And now we have f x of t, y of t, z of t times the magnitude of r prime of t dt. So that's the 3D formula. You see it's the same as 2D, it just has a z component in it, so it's the same. And now I'm going to go to homework, which is about 10 pages of instruction away, to come up with an example. Okay. Problem 32 in a textbook is asking you to calculate the line integral over the curve C xy divided by z ds, where C is a line segment, not a line, the line segment, the line segment between 141 and 363. So these are my values. All right, so what do I do next? Well, the first thing is parametrization. I think we went blue for that, right? We know the line, right? Parametrization for line is x equal x0 plus at, y equal y0 plus bt, z equals z0 plus ct. So these are the parametric equations in R3 for the line. Like 3 linear lines. Each dimension has its own. Now my job is to figure out what these x0, y0, z0, a, b, and c are, so that I can have my line. Well, if you think about it, this is a point in space, that's the point in space, and the line goes through it, but also the vector v, which gives us the direction. So we can quickly find the vector v, which is the vector ABC, if you remember your first chapter, by subtracting these coordinates. So a is going to be 3 minus 1, then 6 minus 4, then I got the 3 minus 1, and vector v, which is the ABC vector, is going to be 2, 2, 2. Our starting point is going to be 1, 4, 1. So x0, y0, z0 is going to be 1, 4, 1. So I have my parametric equations. X equals 1 plus 2t, y equals 4 plus 2t, and z equals 1 plus 2t. So that's my set of parametric equations. We know that we are supposed to plug that into the vector r of t so that we can find the prime later. So now we are on 1 plus 2t, 4 plus 2t, and 1 plus 2t. And now I think I switched to orange to come up with r prime of t. Which are the derivatives? Well, that's 2, 2, 2. That was cheap. And then I need the magnitude, which is square root of 4 plus 4 plus 4, which is the square root of 12, which is 2 root 3. Right, when you square each of the components and you add them, get 12. 12 is 4 times 3. Square root of 4 is 2. So 2 root 3 on r prime. Now, one part that, again, we didn't do here yet is to figure out what are the values for t. Your job is for the line segment to start at 1, 4, 1. So clearly, if t is equal to 0, 0 is going to kill all of these t parts, and you're just going to have 1, 4, 1. And then if t goes to 1, then when you plug in t equals 1 for all of these, 1 plus 2 is 3, 4 plus 2 is 6, 1 plus 2 is 3, so we get the second point. So this part usually is the one that you might have some trouble with, so it's trial and error. But you will figure it out. For circle, obviously 0 to 2 pi if you go to full circle. If you want half of the circle, 0 to pi, and so on. For line segments, you have to play with it, see what works. So I plugged in 0, it wiped all of the t's off, and just have 1, 4, 1, which is the first point. When I plug in t equals to 1, then 1 plus 2 is 3, 4 plus 2 is 6, and so on. So now that I have all of those, I can calculate my integral over the curve C as the integral 0 to 1. And now I have my x times y divided by z. Guys, x, y, z. Plug them in. You know what? Let me choose x, y, z times 2 root 3 dt. So now I'm going to plug in this step, x, y, and z. X is 1 plus 2t. Y is 4 plus 2t. Z is 1 plus 2t. And then I have 2 root 3, and I have dt. All right, great. This cancels completely. So I have kick out 2 root 3, that's a constant. I can actually, let's just do it, 0 to 1. And I have 4 plus 2t. I can factor a 2 and kick it out as well. So that's 4 root 3, 0 to 1, 2 plus t dt. As you can see, the integral is a joke. You just need to get there through all of the hoops before. So 4 root 3, integrate this, you get 2t plus t squared over 2. Compute it from 0 to 1. 0 is going to kill everything, so we don't need to worry about it. We just have 2 plus a half, which is 5 halves. So 4 root 3 times 5 halves. Those guys cancel. And we have a solution of 10 root 3. And that's the area of the curtain above this line. Please look at a book. Example 3 is a nice one, says flight of an eagle, and they give you the C to be 2400 cosine t over 2, 2400 sine t over 2, comma 500 t. I hope you see that's a helix. What does the eagle do? Circles around looking for the prey, and then in a spiral goes down, right? So you can calculate an eagle soars in the ascending spiral path measured in feet, time measured in minutes. How far does the eagle fly over the time interval of 10 minutes? You calculate the length of the path of how many feet it covered. The example is worked out fully in the books you just read. It works out to be 13,000 feet when you write the path. Okay, that's what was line integrals vanilla version. Now we are going to calculate the real stuff. Line integrals of a vector field. Now this is where the fun begins. Line integrals of a vector field. So we start with the definition. Let f with the arrow be a vector field that is continuous on a region containing a smooth oriented curve C parametricized by the arc length. Let T be the unit tangent vector at each point of C the line integral of f over C is the integral over C f dot t ds. At which point you go, huh? And I go, yep. What? What is this? So, before we go in what it is, let's just take a look at every single word of this, make sure we all understand what we have. We have a vector field. We understand what that is. It's just a function that assigns vectors to each point in a space. This is the 2D or a 3D version. It doesn't matter because you guys have the dot product later on. And vector field continuous, that means that those functions that are inside the vector field, they're all continuous and nice. So 1 over x, no bueno, right? Because it doesn't work along the y-axis, for instance. Containing a smooth-oriented curve C. First, the word oriented, because if you remember, your parametric equations have the direction in which they go, orientation. You remember that for the parametric equations of a circle, if you use cosine then sine, you are on a counterclockwise rotation. And if you use sine for x and cosine for y, you're on a clockwise orientation. So oriented curve means, right, that you have to make sure that it's going the right way. The word smooth means differentiable, means doesn't have any of the sharp corners, cusps, or anything where the derivative fails to exist. Remember, you need r prime to calculate the tangent vector, right? The tangent vector is vector r prime divided by the magnitude of r prime, if you remember your formula for unit tangent vector from the first exam. So we need the curve C, which gives us r, ultimately r prime, and then r prime magnitude, so give us ultimately the unit vector t. We need that r to be smooth, meaning differentiable, no corners, cusps, anything, or spikes, where it fails to be differentiable and then creates problems. So no absolute x, absolute y, cones, and stuff like that. So curve parametricized by arc length. Good. Well, we know what the unit vector is. And now finally we get to the point where you have the line integral over the curve C of f dot t. Earlier you had the function times the magnitude of the vector. Now you have the same thing. Remember, unit vector is the vector. We just want its direction. We don't want its magnitude. The function is going to give us magnitude because that's the height of the curtain. And ds is giving us the width of the curtain along the way. So it's the top, right, which is f times the ds. And then the tangent over there is just to give us the direction, which is also coming from c. So that c, we're going to convert into a, b, and then this t, which parametricizes everything to toss it into the domain. I'm going to quickly write down the vector equivalent for this. So the next theorem here is the theorem that we are using to calculate. So to calculate line integral in vector field, use this. So now we have our integral c f dot t, that the arrow and the hat and the ds is going to be the integral a to b of f dotted with r prime dt. Now this is where the notation becomes interesting and funky, so please pay attention. We're going to have, it's a dot product. F contains FGH and R contains X, Y, and Z. So F of X, Y, and Z. Oh no, sorry. Just F of T, easier. F of T, X of T, plus G of T, Y of T, plus H of T, Z of T, all of that dt. So that's the main equation that you're using. All of that can also be denoted as, and this is most of the problems will be given this way, which is this weird notation that we never had before. And to be honest, to this day, I just hate this notation. I just simply, this last line, I absolutely hate it. But anyway, it's a notation that it's used. This is the part that you are using to compute stuff. So you have a vector field, electric, magnetic, gravitational, whatever. You have some kind of field. And that field could be, let's say, there are in this room, obviously. We are all constantly in electric and magnetic fields because the cell phone towers and the radios and so on, they all emit electromagnetic waves so that you guys can have your cell phones and radios and music and all of that stuff. So that permeates, those fields are everywhere. And obviously gravitational field is everywhere as well. So now what I'm going to imagine is I'm going to imagine some kind of line C on the floor, on the XY plane. That's line C. Now that line could be the straight line, parametricized straight line. You can have a circle, you can have whatever you want that you can write the parametric equations for. So you have on the floor this line C, and then I want you to think of a curtain that would go out of that line up, cutting through the vector field. See, the trick is that this line integral will calculate the amount of stuff, right, that is there where these vectors are cutting through this curtain surface. Remember, integrals are calculating accumulation. So how far did the eagle go? That was earlier with the scalar function. Well, the eagle goes 1 foot and then another foot and then another foot, right, as it flies. So foot by foot by foot, it was 13,000 feet flying around, right? So it's accumulation. It's not erasing the data. Oh, you flew for 10 feet and now you're going to fly another 10 feet and the previous 10 didn't exist. No, all of that accumulated on the pile for a total of 13,000 feet for this particular flight. The same thing for the area. If I want to calculate the area of this wall, I can do it in two different ways that I can think of right now. One is to measure, obviously, and be done. The other way would be to just measure one brick over here, well, the cinder block, and count how many there are and multiply by the number of how many there is. Right? So integral is accumulation of all of these put together, right? So in the same sense, in the vector field, you are going to have air moving, you're going to have water moving, you're going to have electrical or magnetic, gravitational field, right? So you just want to know how much stuff is there along the line that you are thinking, that you're looking at. So, and it needs to be consistent with orientation. So there's this cool picture that you can take a look at the, over here, this is a 2D case. You have a vector field y minus x and x. And as you can see, it's something like this. So maybe you have some kind of rushing water like this and then just all piles up together and it creates this flow right this way. So that could be just looking on top of the water moving. And then let's say you want to take a path through that water like this right here, right? How much work you need to do, right, to battle through this, right? Because over here the water is helping, so it's kind of pushing you, right, for a little bit, and now it's hitting you on the side, kind of trying to push you this way, and now you're going against the current. It's really hard, right, to move this way. So you can calculate the amount of work you need to push to cover this distance, and this distance is this quarter circle from 0, 1 to 1, 0. You can see the arrow. Now this arrow, as you can see, this is a clockwise, so in our parameterization, we better have sine first and then cosine. And there it is, r is equal to sine first and then cosine, right? Because arrow, remember in our definition, the word oriented is a very important word. So the word oriented, make sure that this arrow is pushing this way. So that's what we have in case of this. Now, obviously you can go the other way. If the field is symmetric, then you will have the same struggles. It's going to start easy because the water will be pushing, then it will be pushing you on the side, and then you will go against the current completely, so it will be tough to kind of finish off the journey. The orientation is important, guys, because whether you're going to the left or to the right or up and down, whatever on the picture, it changes your equation for r. And r changes the equation for r prime, and r prime changes the direction for the t hat, right? So it is important to have the right parameterization, the right equations for the situation you have. And then the rest of the problem is just, plug and chug. I think that the next two examples are the ones that we would like to take a look. Okay, so here's the work integral. Awesome. So work done in a force field. It shouldn't be any strange to you that you have two magnets and then you take north to a north, they repel. So you put a magnet, you glue the magnets to a little block or something to, don't do it to cell phone, but if you put a little magnet there and take another magnet, if this one is facing north this way, you take another magnet facing north, so north into north, it will push the phone, and then, so what happens is that one of the magnets has its magnetic field, the other one has its magnetic field, and then they interact. So you can push stuff through magnetic field. So force done by vector field, guys, we have the 100% of all objects that exist affected by gravity. The effects that we see are only on a large scale. So we do see the sun attracting the planet. We see the planet attracting us. What we don't see is the gravitational field that works in between us, because the gravitational force is extremely weak force. It's ridiculously weak. We are able to lift the objects against gravity. Now, obviously, the more massive the object is, the more force is needed to exert to lift the heavier object, but still, we can beat these. Now, also, you can separate certain magnets by hand. You can even deal with some electromagnets that you can split by hand, but magnetic force, electromagnetic actually is one and the same. Electromagnetic force is much, much stronger than the gravitational force. And then you have forces like the strong nuclear and weak nuclear force, which are holding atoms together. And those are insanely powerful forces. We use them, obviously, to split atoms in the nuclear fission and create either electricity or the explosion. But believe it or not, those thermonuclear plants are only 5% efficient, and they produce more electricity than we ever need. At 5% efficiency, they produce more electricity than we will ever need. In comparison to solar farms that are actually not as good as you would think. They call them the green farms and all of that stuff, but most they do is killing birds and just sit there and take up land. So farmable and livable land. And the wind guns are just much worse. They just shred everything that goes through them. So that's why there are no birds anymore. Go find one in New Jersey somewhere. You know how many solar farms we have, right? Do the research. See how terrible they are, actually. And then you might change your opinion. So now, when you look at the work integral, through the vector field, right? The work integral, W, would be the same deal. You have the work integral, which is the force times the tangent vector ds, which would be given by the same AB force vector, which is the vector field, right, times the magnitude of r, t, dt. I'm just going to label this as work. And now we're going to take a look at the example with numbers, which would make a half mark for our lecture, because we still have to do circulation and flux. All right, so let's take a look at the example of problem for work. Let's find something that has there we go, finally. So it doesn't really matter. These are all those problems are the same, just different numbers. 51 gives you the vector field, which is given as yx. This is not a rotational field because it needs a minus. On the parabola, y equals 2x squared from 0, 0 to 8. Okay, let's take a look at this together. So problem 51 has the vector, the force field, right? So I'm just going to label this as a force field. I don't care if you're using electric, magnetic, gravitational, whatever. Stuff moves in the field because the field is the one that's pushing things, right? All those invisible vectors, right? So that's the force field, and this is the path, right? Which is the vector c. So we start with the parametric equation, and so parameterization first. The dummy parameterization is okay. X equals t, y equals 2t squared. If you are not sure what the hell is going on with these parametric equations, please go back, watch the 12.1 video, the first lecture of Calc3, or go back to my Calc2 and look for parameterization in there. Now, you might have to, because the book switched the sections, look for 10.1 older videos. I believe I only have one that it's in the new 12.1. Maybe only one 12.1. But you look for 10.1, parameterization, or look by parameterization in the title. Parametric equations, that's the title. So this is called the dummy parameterization because you are just replacing x with t, and here is the, again, x replaced by t. So now that makes a set of parametric equations. T clearly starts at 0, because when you plug in 0 for both t's, you get 0, 0 for x and a y. And then t goes to 2. When you plug in 2 for t, you get x equals 2, which is that one. And then plug 2 over here. 2 squared is 4 times the other 2 is 8, which is that one. So you have to play a little bit about with this to get it. So that was our blue to find parametric equation. Our orange, which is the r prime, would be the, well, so first let's find r prime. R first, that's t, 2t squared. Now, so that's r, sorry. Then r prime is the next, which is 1 and 4t. And then r prime magnitude, which is square root of 1 plus 16t squared. Holy nightmare, that took me forever. So we have our r, which is just parameterization, then r prime, the derivative of it, and then r prime magnitude. We got that. Now we have our f. We need f of t. Now f was given as yx. To put that in terms of, here is your x, here is your y. So we plug that in as y is 2t squared and x is t. There we go. Good. Perfect. We are ready. Our work integral is going to be integral over curve C f dot r prime magnitude dt is going to be the integral 0 to 2. My f is 2t squared t and dotted with the well, we can do 1 for t. So which one should we do? The we can just do that one, dotted with r prime. Yeah, we can just do it dotted with r prime. So 1 and 4t in a dot product, and then you work it out. 0 to 2, the dot product is going to kill the vector, so we have 2t squared plus 4t squared dt. Altogether that's 6t squared, 0 to 2, and now we integrate to give us 6t cubed over 3 from 0 to 2. These guys cancel, so we have 2 times 8 minus 0, 16. And the problem doesn't give us units, so we can call it Newton meters or feet foot pounds, whatever. They did not give us any work done to move an object on a given oriented curve. They did not give us units. So Newton meters, whatever. I'm from Europe, deal with it. Good. So from this calculation, we see it's I don't want to call it straightforward because nothing is straightforward. You have to sit down and really dig into these. But if you pay attention what's what, you will be able to decode what plugs in where. So it's just a lot of plugging in. Main equation is holy nightmare, guys. X prime, y prime, z prime, it's r prime over here. Holy nightmare, I forgot primes in the main equation. That would make everything wrong you ever do. Make sure you have in the main equation all the primes. It's not a prime. Holy nightmare. Terrible. I know. Going back to teaching Algebra 1. They have no primes there, so I don't have to worry about these things. That was terrible. R prime are these three. All right? And the F prime are your definition for the vector field, right? FGH, that's your FGH, that's your F. The dot product, multiply each of the components, just add them together. That's the dot product. So that's it. All right. Managed to get through the first half of the lecture, and now the two parts that count a lot: circulation and flux. Now, I think I told you a story at one point what happened with that one interview for a research position at Exxon, I believe. Or I maybe told that story to just few of you. They asked all of the people who applied to calculate flux. It's a very important concept. So we're going to learn about flux and calculating flux. First circulation, then flux, and then lunge. So circulation. Definition. Let F be a continuous vector field on D in R3. Okay, so this is specific. This is specific. Let C be a closed, I want to circle that one, closed, I mean underline, closed smooth oriented curve in D. The circulation of F which is circulation of the vector field on C is the integral, line integral C, F dot T. So this is just your standard vector that we just calculated so far, where T is the unit tangent vector, where T hat is the unit tangent vector to C, consistent with orientation. Two examples will illustrate what this means much better than any words that I can master right now. So let's take a look at two of these. The first one is going to be the vector field given as a radial field xy over unit circle. So we just calculate the stuff the way we have seen it. So again, color coding over here, starting with parameterization. We have a unit circle, so we know that by now R is given as cosine T, sine T. Right? So that's counterclockwise rotation. We have our R. That's the part you memorize. Unit circle is that. Done deal. Now R prime is negative sine T cosine T, and then magnitude of R prime is 1. You guys square those and add them, so that's fairly simple. And now to calculate the integral C of F dot T ds would simply be, I keep forgetting writing this because I know it, but then you need to have it, 0 to 2 pi. Make sure you include because those are your A and B limits. So 0 to 2 pi, and now you can use vector forms if you want. You have your xy vector dotted with R prime vector, which is negative sine T cosine T, and we have dt. Now you have a lot of plugging in to do, so be very careful. Your x is given with the cosine T, so that's going to be cosine t, and your y is sine t, so that's sine t. Your x and y are here. In R. R tells you what x and y are. Dotted with negative sine t, cosine t dt, and you have the integral 0 to 2 pi of a big fat 0 dt, and we have 0. See, cosine times negative sine is negative sine cosine, sine times cosine is positive sine cosine. When you add them, they add to 0, so we get a big fat 0. Circulation of a radial field is 0. Now I'm going to do the same problem, except I'm going to use rotational field. So instead of radial, I have rotational field now. We can use F equals negative yx on unit circle again. And that one is going to give us our F equals negative yx, and our R is equal to cosine t sine t, which will give us our R prime as negative sine t cosine t. I stopped color coding this stuff and so on. We're just, what is this thing? All right. So what we have is our integral, and this is also, how do I get rid of this? This over here is on 0 to 2 pi. It's a circle. So 0 to 2 pi, we have our negative yx dotted with negative sine t cosine t dt, which gives us integral 0 to 2 pi. My negative y, that's negative sine t cosine t dotted with another negative sine t cosine t dt. When I do the dot product between these two vectors, I get sine squared t plus cosine squared t dt, and the whole thing is just integral dt 0 to 2 pi, and you get 2 pi. Circulation of rotational vector field over the unit circle is 2 pi. It's time for us to draw again these two and take a look at what we have. For the radial, first off, I have a unit circle on both of these. That's my C. For the radial, I have vector field doing this. So we see that along the curve C, which is counterclockwise, they don't agree at all. Where the rotational field and the circulation, if you remember, looked like this. Do we see the spin? And that's a rotational field. Radial field, rotational field. So circulation is going to calculate the amount of spin that you have on top of the, think of a tube, think of the hurricane going like this, right? And moving, this is the land, so this should be on the floor, right? So the hurricane would be here, spinning around like that. Tornado, whatever. It's explosion. You can also think of a sun radiating in all directions. Radiates out. There's no rotation in it. There's no rotation here. It just radiates energy everywhere. Explosion of a grenade. There's no rotation in it. It's just particles going in all directions away from the center of the explosion, right? So that's radial. Rotational spins. Now circulation, circulation, right? Stuff is moving. So over here, there's no rotation at all. Radial field, circulation is 0. Over here we get 2 pi, so we can get to quantify that spin. So that's our circulation. And 2-dimension, 3-dimension, they all get to be the same. You just have an extra calculation. And the last one, which we're cutting it close, is flux. Definition. Let vector f, which is a vector field of fg, be continuous vector field on a region R of R2. Let curve C, parametricized by R of t, which is good old x and y, x of t and y of t, for a less equal than t less equal than b, be a smooth oriented curve in R that does not intersect itself. So square is okay, circle is okay, number 8 not okay. The flux is of the vector field f across C is, and now you have the f dotted with vector n. Hello, unit vector n. The s, luckily we don't have to use it because we can just work out f of t y prime of t minus g of t x prime of t dt. This time I did not forget the primes. Where n is the t cross k. a unit normal vector. We know all the other players. It's the part of the definition. I'm just going to do it in different color. If C is a closed curve with counterclockwise orientation, N is the outward normal vector, and the flux integral gives the outward flux. Huh? Okay. Not a big deal. Have you seen a fan? The bigger the fan, the more air it pushes through. Smaller the fan, less air, because the blades are shorter, right? Those blades will have the span of, let's say, 1 inch for the little fan that you put on the side of your hat just to point in your face when you are at the graduation baking for like 20 hours because it's inefficient, right? So you take you have that hat with a tangent plane on it, right? And you attach a little fan and it just blows in your face. So it's going to be unit circle how far those blades reach. Take the industrial fan with a 1 meter span propeller radius, so the propeller is as big as I am, because I'm almost 2 meters tall, right? So the fan would be, the blades would be pretty much as big as I am. Well, that can push a lot more air. See, the amount of air that will go out perpendicular, which is why we have the N, woohoo, right? Perpendicular to the surface, or orthogonal to the surface while the blades rotate. The bigger the curve C, which is parameterization. Remember, if it's a unit circle for 1 inch, or unit circle for 100 inches, right? The bigger that circle, the more stuff goes out. It calculates the amount of stuff that that area brings out perpendicular through. What can you do? You can cut the garden hose and the water will be going perpendicular out. That water is a vector field, right? Your circle of the hose would be the edge at which you are looking, right? And then the water will just push through at whatever you made the cut, right? So you can do that with a pipe, you can do that with everything else. Now in the vector field, the same thing happens, right? Because the vector field is everywhere around us, and then the wider you are, right, the more surface area you cover. Let's think of a tank. Tanks are extremely heavy because they have all of that heavy-duty steel shielding on the side, so you can't, right, shoot at the tank with regular bullets and stuff. You need some anti-tank stuff. What do they have? They have little wheels, like your cars? No, they have those huge tracks on both sides. They're really wide. Why? Because through gravity, right, as the heavy tank is pushing down, there's more surface area, right, to make the contact between the surface and so it doesn't sink into it. Just made the whole tank and put it on the wheels for train, for instance, it's not going to go anywhere. It's just going to dig in the ground right away, right? The trains and carry the same weight, so those wheels can withstand the weight of a tank. That's not a problem, right? The problem is that those wheels are not wide enough to put them on the regular ground or the asphalt road or a sand or something where the tracks can deal with it. So the flux, right, calculates the amount of stuff that goes perpendicular, right, to the surface that you are looking at. That surface is going to be bounded by C, which is required to be closed, right? So C has to give you a closed area. So you can think of a print. If you are to take a tank and just push it in a sand and just lift it up, right? You're going to see two rectangular track where the tracks made the impression, right? That's the surface area enclosed by C on which the gravity was dealing to push the tank up, right? So it doesn't sink into the ground. Remember, the way you sit on a chair, your weight pushes down, chair pushes the same normal vector, pushes the weight up, and then they equalize and you're able to sit. If the chair is not structurally found, as I found certain chairs for me because I'm 270 pounds, when I sit on a chair which is not structurally found, right, my weight is stronger than the normal vector of the chair, and the chair breaks. It's very simple, right? It's very simple physics. So now we are calculating stuff that is perpendicular to the surface, which means that the two examples we did earlier are going to flip now, and the radial field should give you, right? A radial field should give you maximum values, and the rotational fields should give you 0. Because rotational fields spin, and there is nothing going on in terms of perpendicular escape. Let's take a look. So, radial field was, vector field was given as x, y, don't forget the arrow, on unit circle. We have all of our usual suspects, right? R is going to be cosine t sine t, and for the first time, 0 to 2 pi immediately when I put parameterization, right? And then we have our friend R prime, which is negative sine t, sine t cosine t. And we have our f in terms of these guys. So x is going to be given as a cosine t, and sine will be in y slot. So now, to calculate our vector f dot n ds, we'll have our 0 to 2 pi, and now we have f, which is given by x, which is cosine. So, guys, this is your x, this is your y, and this is your x prime, and this is your y prime, and this is your f. And no, why do I have f prime over here? Just f. There's no prime here. I don't know why I put the prime there. I just deleted the prime. If you have a prime there, just kill it. So those are your f and g. So f is a cosine t time y prime, which is another cosine t, minus g, which is a sine t, times negative sine t dt. There we go. And as you can see, 0 to pi, this is just sine squared t plus cosine squared t dt, which is integral of dt, 0 to 2 pi, and the whole thing is 2 pi, and you guys have the radial field now give us a value. Now I already said, spoiled it, rotational field should give us 0 in the same calculation. Okay, let's see. So rotational field, we have F equals negative yx on unit circle. And again, R is going to be cosine t, sine t, t between 0 and 2 pi. R prime is negative sine t, cosine t. And our F, no prime, F is negative y. So that's going to be negative sine t. Remember, this is your x, this is your y, this is your x prime, this is your y prime. So I need negative y. So that's going to be negative sine. And then comma x, x is cosine t. Our line integral f dot n ds is going to be 0 to 2 pi f. These are my f and g. That's the same f and g, but we have to write them in terms of parametrics, which is why I have the last line. So my f is negative sine t, needs to be multiplied by y prime, which is cosine t, dot product, so plus. And now we have a g, which is cosine t times x prime, negative sine t. Oh, something is wrong over here. They should cancel. They're not canceling. F y prime. Oh, it's a minus over here. Holy nightmare. All right. It's a minus right there. So we have 0 to 2 pi of negative sine t cosine t plus sine t cosine t dt, which is the big fat integral of 0, and it gives us 0. So we are not expecting to get flux out of rotational field, because rotational field doesn't give anything out. It spins all the stuff inside. So if you are thinking about the sun is radiating energy perpendicular out in all directions around the sphere, around the ball, all directions, and each single one is perpendicular to the surface of the sun. It's from the origin of the sun, the ray goes out. Whenever that ray hits the surface of the sun, it's going to be a tangent plane. You can generate a tangent plane at that one point. So all of these lights, all of these rays that come out of the sun, that's all radial. And that's a three-dimensional radial field. The other one would be an explosion of a grenade or something that is, again, going radially in all directions. And then for rotation, right? Rotation is a little bit different. You're thinking about the hurricanes, you're thinking about tornadoes, you're thinking about, you can also think rotation of the earth, right? As it spins, and so on. It does not radiate anything out. It keeps all of its stuff right there. And that's why there is no outward flux, because it's not giving out energy out of the system. So those are the concepts. There are a whole bunch of homework problems. Now you will find fields that are a mixture of the two. So it's one or the other. These are extreme cases, right? Two ends of the spectrum. So everything in between will have a little bit of rotation, a little bit of the circulation and a little bit of a flux. So that depends on what configuration you get. You follow your calculations, and you will get how much spin and how much radiation you get out of these fields over the curve you picked. Bye.